Alright guys, so in this video we're going to review some practice problems really out of Lecture 4. We might touch a little bit on Lecture 5, but for the most part we're going to focus on Lecture 4. Root mean squared speed is essentially the velocity that molecules move, but we call it the root mean squared speed, and you can see the derivation in the video. But root mean squared speed, which we represent as V, RMS, or mu, so it's like the micro, that's another way to represent root mean squared speed, but root mean squared speed is equal to the square root of 3 times r times t all over the molar mass. So it's 3RT all divided by the molar mass. Some important things to know here is that R, the R that we use is 8.314 joules over mole Kelvin. So this is the energy R. We use the energy R here because velocity is related to the joule. When we are doing any root mean squared calculation, the R has to be the 8.314 and your molar mass has to be in kilograms. That's going to be super important, so make sure you have that written down. Your molar mass has to be in kilograms. So let's go ahead and calculate the root mean squared speed of the molecules in a sample of N2 gas at 25 degrees Celsius. My VRMS is equal to the square root of 3RT over my molar mass in kilograms. So what I want you to do is see if you can set this problem up, putting in your R, be careful with your T, check your units, and putting in your molar mass in kilograms. Let's see, we get 3 times 8.314 times 25 degrees Celsius is 298 Kelvin. Don't forget to convert Celsius to Kelvin. All divided by, so I'm going to do this down underneath just to make sure we've got the right information. So N2, not just one N, but two N's. So we have 14.01 times 2, which is 28.02 grams per mole. But we need kilograms, so 1, 2, 3, and I get 0.02802 kilograms per mole. And again, the reason is because a joule is equal to a kilogram times meters squared all over seconds squared. And so that's why we have to use kilograms here, because we're using joules. So if we plug this into our calculators, we do 3 times 8.314 times 298 divided by 0.02802, and then take the square root of that entire thing, and you get 515 meters per second. So I got 515 meters per second. And again, that's because root mean squared speed is velocity. Velocity's units are meters per second. So that's how we go through and we calculate root mean squared speed. Now, some things to remember. See if I can have some space to write this at the bottom. As molar mass increases, so as your molecules get heavier and heavier and heavier, your root mean squared speed decreases. Right, so think about if two people are racing down the hallway. The smaller one probably is going to win. The smaller gas molecules always win. Heavy moves slower. So if you have any questions, make sure that you let me know. But this is looking at a root mean squared speed calculation. So now what we're going to do is we're going to look at effusion versus diffusion. Diffusion. Diffusion is looking at how gas particles mix with each other. If something diffuses well, that means it mixes well. So you can think about gas particles in a room. Effusion with an E is how gases react over time, because effusion is about how a gas can escape through a small pinhole. So if we look at this balloon over time, both gases effuse through small pinholes, but the lighter gas actually effuses faster, because remember, like we said, lighter moves faster, and the faster the gas moves, the faster it will escape through a balloon. This YouTube video shows how Graham's law is demonstrated, shows this animation. This is going to be very important because you will see this example over and over. So if we have colorless ammonia, gas, and colorless hydrochloric acid gas, it actually forms ammonium chloride. So here's a glass tube. What we can do is we can take some hydrochloric acid and some ammonia, We'll put cotton balls in both ends of this glass tube, and we can add some HCl to one end and some NH3 to the other. So we put the liquids on, but those will vaporize into gases. So we put them on, we drip them on each side, and then they vaporize into the gas. And so what I want you to do is just predict where the ammonium chloride will form. Well, notice how it doesn't form in the middle. It forms closer to the HCl. Well, what I want you to do is I want you to think about, why does it form closer to the HCl? Well, it forms closer to the HCl because the HCl has a higher molar mass, so it's not going to move as fast. The ammonia has a lower molar mass, so it's going to move faster, and so they're actually going to meet further down the tube. Okay, so what I want to do is I want to look at a calculation that deals with Graham's law. And so this deals with rates of the movement of gases and their molar masses. So this says an unknown gas comprised of diatomic molecules effuses at a rate that is 0.355 times the rate at which O2 effuses at the same temperature. Calculate the molar mass of the unknown and identify it. So we don't know the gas, but we know how fast it effuses, and we know that we're also dealing with O2. So let's just write the equation for Graham's law. So Graham's law says that the rate of gas 1 over the rate of gas 2 is proportional to the square root of the molar mass of gas 2 over the molar mass of gas 1. So this fraction of rates is proportional to the square root of gas 2 over gas 1's molar mass. So now let's just plug in some numbers that we know. So we know that an unknown gas effuses at a rate that is 0.355 times the rate. So I'm going to say rate 1 is my unknown, rate 2 is my O2. Because what we know is that rate 1 is essentially 0.355 times that. So if that's 1, my unknown would be 0.355 times that. And that's equal to molar mass of gas 2, which we said was the oxygen. So that's 32 grams per mole over X. Now this is where you have to be really, really careful with the math behind this. Be careful with your algebra. So to start, I'm going to square both sides. So once we squared both sides, we're going to get 0.355 squared equals 32 over X. Now we need to get X on a side by itself. We can't just divide by 32 because that's going to leave us 1 over X. So I'm going to multiply both sides by X. And I'll divide by this 0.355. So I'm going to get X equals 32 divided by the quantity 0.355 squared. Now put that in your calculator and see what you get. I got 253.92 grams per mole. So that's the first part, is calculating the molar mass. Then what we have to do is we have to identify this gas. Now you might be looking at this saying, well, how in the world do I identify this gas? Well, we know that it's composed of diatomic molecules. So if we know it's composed of diatomic molecules, that means we really only have certain gases to choose from. Ron, H, Cliff. So what we need to do is we need to figure out which of these masses, when multiplied by 2, gives us this unknown. So if you work your way through and figure it out, what you find that the gas is I2. Okay, so that's dealing with Graham's law of effusion, which again sets our rates proportional to the molar masses. You just have to remember that it's opposite. If it's rate 1 over rate 2, that's equal to the square root of molar mass 2 over molar mass 1.